I am going to give one more example. This has 3 states, and this is a state transition diagram, and the values are nothing but the rates in which the system is moving from one state to other states. So, that is the difference between the state transition diagram of DTMC and the CTMC. So, this is the rate in which the system is moving from one state to another state, and some arcs are not there. That means there is no way the system is moving from the state 2 to 3 in a small interval of time, whereas all the other possibilities are I have given. So, the corresponding Q matrix is a 3 cross 3 matrix, and you can make out all the row sums are going to be 0, and the diagonal elements are minus of sum of other values in the same rows, and other than the diagonal elements the values are greater than or equal to 0. My interest is to find out the time dependent solution for this example also. I can make a forward Kolmogorov equation. P dash of t is equal to P of t times Q. It is a 3 cross 3 matrix, therefore, I will have 3 equations, and I have one equation. I can have a summation of probabilities equal to 1, and I can start with the initial condition, the system being in the state 1 at time 0, that probability is 1. I can start with that, and I can solve those 3 equations with the initial condition, and I can get the solution. That is a one way. Since it is a finite state CTMC, there are many ways to get the time dependent solution. Basically, you have to solve the system of differential equations with the initial condition. Here I am using the eigenvalue method. That means find the eigenvalues for the Q matrix. Therefore, use the eigenvalue and eigenvector concept and get the P11 of t with the unknowns k1, k2, k3. And to find the unknowns k1, k2, k3, use the initial condition. Here I am using the initial condition as well as the Q matrix values. The Q11, that means the element corresponding to the 1, 1, that is nothing but the P dash of 1, 1 of 0. Similarly, if I go for Q square matrix and Q11 of 2, the element in the 1, 1 in the Q square matrix, that is nothing but P double dash of 1, 1, 0. Therefore, now I can use these 3 initial conditions to get the unknowns value k1 and k2, k3, k1, k2 and k3. So, once I know the k1, k2, k3, I can substitute. Therefore, the P11 of t is equal to this much. Similarly, I can go for finding the P1, 2 of t and P1, 3 of t. I do not want P1, 3 in the same way, because once I know the P1, 1 of t and P1, 2, t. So, 1, 3, t is nothing but 1 minus of those 2 probabilities, because the summation of probability is equal to 1. So, this is the other way of getting the time dependent solution, the transition probability of system being in the state j, given that it was in the state I at time 0. Suppose the CTMC has the finite state space, then I can use the exponential matrix also to get the time dependent solution. That is what I have given this way. So, start with the forward equation. Therefore, the solution is going to be P of t is equal to P of 0 e power q of t. P of t is a matrix, P of 0 is the matrix, e power qt, that is also again going to be a matrix, exponential matrix. Therefore, I am writing e power qt is nothing but q is the matrix and the t is the real value. So, greater than or equal to 0. Therefore, e power qt is going to be the I matrix. I matrix is nothing but the identical matrix of order whatever the state space number, plus the summation I is equal to n is equal to 1 to infinity of q power n times t power n divided by n factorial. So, that the whole thing is going to be the exponential matrix, and using that you can get the P of t. That's a, I am not going detailed for how to compute this e power qt and so on, but whenever you have a CTMC with a finite space, through this method also one can get the time dependent solution. So with this I have completed the examples for the CTMC to find out the time dependent or transient probabilities. Now I am moving into the limiting distribution. The way we discuss the limiting distribution for the CTMC, the same concept can be used for the CTMC also. The change is instead of the one step transition probability matrix, here we have to use the infinitesimal generator matrix in a different way. So I am first giving the ergodic theorem. Whenever the CTMC is irreducible, that means all the states are communicating with all other states. Since all the states are communicating with all other states, if one is of the particular type, it is a positive recurrent, then all the other states are going to be a positive recurrent. If one is going to be a null recurrent, then all the other states also going to be a null recurrent. So here I am making the assumption the CTMC is irreducible as well as all the states are positive recurrent. Then the limiting distribution always exists. Suppose it is independent of an initial state, it need not be a independent of initial state. Suppose the same thing is independent of initial state, then I can write that limiting probability is a Pij of t. Since it is independent of I can write it as the pi j. Then I can form a vector, and since it is a limiting distribution, it is a probability distribution. Therefore, the probabilities are, these probabilities are always greater than or equal to 0, and the summation of probability is going to be 1. It won't be defective, it won't be less than 1. That's the Ergodic theorem says. Whenever you have a irreducible CTMC with all the states are positive recurrent, then as t tends to infinity, the system has the distribution, limiting distribution. If it is independent of initial state, then you can label with the pi j as the probabilities, and this probability distribution satisfies it's a probability mass function, therefore it satisfies the probability mass function conditions. That means whenever you have a dynamical system in which it is a irreducible model and all the states are positive recurrent, that means the mean recurrence time is going to be a finite value, then that system is called it as a ergodic system, or the ergodic the concept can be used. Therefore, as t tends to infinity, you can get the limiting distribution. If it is independent of initial state, means whatever be the seed you are going to do it for the discrete event simulation for the dynamical system, that is ergodic, for a ergodic system, then the initial condition seed does not matter to get the limiting distribution. Later we are going to give some few examples how to find out the limiting distribution. I am explaining the stationary distribution also. The stationary distribution, the way I have explained the DTMC, the way I have discussed the DTMC, the CTMC also same. So I have a vector, if the vector satisfies these three conditions, probabilities, therefore greater than or equal to 0, summation is equal to 1, and you should be able to solve this equation and get the pi's. It is a homogeneous equation. So you need a second condition to have the non-zero probabilities. So if you solve pi q is equal to 0 along with the summation of pi j is equal to 1, and if these pi j's exist, then the CTMC has the stationary distribution. The similar way I have discussed the stationary distribution for the DTMC model also. Instead of pi q is equal to 0, we had pi p is equal to pi. So if any vector satisfies that pi p is equal to pi and summation of pi a is equal to 1 and all the pi a's are greater than or equal to 0, then that is going to be a stationary distribution for DTMC. The same way, if pi q is equal to 0 and pi summation of pi j is equal to 1, by j is equal to 0, if this is satisfied by any vector, then that is going to be the stationary distribution for a time homogeneous CTMC. Every time we are discussing the default CTMC, that is a time homogeneous CTMC. The main result for the stationary distribution, whenever you have a irreducible positive recurrent CTMC, the stationary distribution exists and that is going to be unique. Whenever the CTMC is a positive recurrent as well as irreducible. There is no need of periodicity in the CTMC, whereas the same stationary distribution, the stationary distribution for the DTMC, we have included one more condition, that is aperiodic. But for the CTMC, there is no periodicity for the state. Therefore, as long as the system is irreducible and a positive recurrent one, then the stationary distribution exists and it is unique. And by solving these equations, you can get the unique stationary distribution.